8 bits each of them, because that's the size of the S-box. And as a result, the adversary who sees that can really do divide and conquer and recover the key by repeating 16 times an attack of complexity 2 to the 8, rather than having an attack of complexity 2 to the 16 times 8, so 128, which is the expectation for key recovery. What Paul Kocher and co-authors found out is that with leakage, in fact, you have information about this very place where the block cipher is extremely weak. So you have information about the first round. Here I will even show what happens with the first S-box. So you have a plain text xi, you XOR it with the key k, and you have intermediate values y and z before and after the S-box. And when you do these operations, you receive these power traces that I put on the top. So this is just the power consumption of the device. And what we know is that this power consumption and many other types of leakage are actually correlated with the intermediate computations. It's not exactly the target intermediate value that you will receive. So it's not as simple as the black box attack I just described after one round, but it's quite strongly correlated with this. And therefore, what the adversary just has to do is to model the leakage. Okay, so for every target intermediate value, you will try to model what should be the power consumption for this key candidate. And you will compare this with the actual leakage, with the real measurements. And if the model is behaving is good, I would say is properly estimated and is accurate enough, then by comparing the 256 model that corresponds to 256 key candidates with the single leakage vector that you have, which corresponds to the real measurements for the correct key, you're actually able to recover one subkey candidate. And then you just repeat that 16 times and you have the key in full. So that's it. What directly comes up from this attack, and what kind of was the beginning of our questions, is the problem of how to evaluate these attacks. If you see that, I mean, you have multiple problems, but mostly you have the problem that you have a statistical evaluation based on a model that maybe does not perfectly represent reality. So how it was going when we started to discuss in 2004-5 is typically that both adversaries and evaluators were trying to launch an attack with an arbitrary distinguisher, and the result of the attack would, like the correlation attack that I mentioned, would typically look like in this figure. So on the x-axis you have the key candidates, you have 256 ones. On the y-axis, you have the correlation coefficient. And as you can see, by monitoring this correlation coefficient, you're able to see that there is one key for which it is really better. And that's probably the correct value of the key byte you're looking for. If you do that, I would say as an adversary that gives you the key, as an evaluator, it's not so nice, or as a designer, it's not so nice because it gives very limited or even no statistical confidence at all. So first thing that you can do is, of course, repeat the attack many times and estimate a success rate, a probability of success, or there's different ways you can call this. And that would give you this type of curve, which is already more informative, right? On the x-axis, you have the data complexity, and that's the number of traces that we measure. On the y-axis, you have the success rate, and what do you see is that by increasing the number of measurements, in the end, the adversary is able to recover the key with very good confidence. So that's better from the statistical confidence viewpoint. It's still not perfect, essentially because your adversary can still be quite suboptimal. And that deviates from the typical goal of cryptographic research, where we want to, or ideally, we would like to have security that depends on the I would say, the complexity of the adversary measured in number of traces, for example, not on the adversarial strategy. And like I would say from the engineering viewpoint, you had then these improvements of attacks that I picture a little bit on this figure. So based on the first adversary, you can try to change a little bit the model to improve the statistics, to use more dimensions. There's many ways that you can use to improve the attack. And hopefully at the end, you get this black curve, and that would be the optimal, I call it here the optimal template attack. So that's typically what we hope being able to evaluate. Good. So that's, I would say, what was driving us. And to be complete, it's important to say that that's not the only question that was running at that time. Another important question was to find out whether these attacks were practical. And originally, and maybe still today, that really created a situation where you had a kind of wall between the two approaches. The one that I just mentioned, so the one where we try to find out what is the optimal attack, what is the worst case security level, really has the goal to formalize and to develop long-term security and to have implementation security as connected as possible with cryptographic research. So this is typically important if you want at some point to incorporate physical leakage in security proofs. That's typically in this worst case model that we are going to work. And very summarized, I would say that what we do there is to try to apply Kerckhoffs's laws at the implementation level, which typically means that when we are in this setting, we give everything to the designer and the evaluator. We give the source of the implementation. We give the circuit layout, everything. We maybe give the randomness that we use in countermeasures during the preparation of the model, so in an offline phase, so that the adversary really understands the device he has in his hands. The other approach, the approach of finding out whether these attacks is practical, this was much more driven by industry, evaluation and certification schemes. And I would say the goal is quite different. The goal first was to fix an emergency situation efficiently. And for this, what was developed is this idea to rate the attacks based on the adversary's potential. This even goes, I would say, nearly against the optimal attack, because if you look how these certification schemes work nowadays, for example, the fact that the implementation is secret is valuable for the security rated by these schemes of the implementation. Essentially because they think if an attack requires details about the implementation, they rate this as a more difficult attack. And that's it. So we were with these two parts of the wall. I would say the rest of the talk will be mostly about the top part, this question of optimal attack, but I will also come back a little bit on whether there's really a wall in between, and that's part of the important open questions, I would say. Cool, good. So what is this evaluation framework? Essentially, we wanted to formalize what is a worst case attack. And for this, we tried, I mean, that was quite natural, right? We had an implementation with a communication channel that the adversary could monitor, and that's typically where the plaintext and the ciphertext would be sent. And then you have this side channel going through another scope, and that's this additional information that the adversary gets. That could be the power consumption, that can be the electromagnetic radiation, and so on. And probably the most important part that we have in this paper is this idea of having a conceptual separation between two types of metrics. On the left, you have IT metrics, standing for information theoretic metrics, like the mutual information or the perceived information. On the right, you have security metrics. And essentially, the idea is that information theoretic metrics, they are independent of the adversary's computational power. So they really aim to measure the amount of information that you have in the leakage. The security metrics, like the success rate or the guessing entropy, they depend on the adversary's computational power, and they rather aim to evaluate what the adversary can do with this information. Good. And if you start there, I would say a first question is, of course, why do we need two metrics? Because if you think about it, I would say security metrics are in a sense more complete. And you could question why we don't directly go for worst case success rate or guessing entropy all the time. The problem that we face here, and that I try to represent with this figure, is that they can be quite expensive to estimate, and maybe sometimes not so easy to manipulate with good intuition. So what you see on the figure is you have an axis with the M value, which is the number of traces that you need to train the model. And you have an axis with the N value, which is the number of traces that you need to attack with the trained model. And then you have this 3D curve, which is the success rate. So estimating that takes quite a lot of time. And as a result, the reason why information theoretic metrics can be interesting is that they can enable much more efficient evaluations. And probably also evaluations that are easier to interpret, because in a sense they can really be viewed as the learning curves of a machine learning algorithm. So what can you learn from these metrics? So here what I what I put as a figure is a figure where you have an information theoretic matrix, which is the perceived information on the y-axis, and you have the number of traces that you need to profile the model, so to train the model on the x-axis. And what I claim is that this contains most of the information that you see on the previous figure, because if you look at the x-axis, and for example, if you look at when the perceived information becomes positive or when the perceived information saturates, this tells you about the profiling complexity of the model, or the training complexity. That tells you how many traces, how many measurements do you need in order to be able building a model that is informative. And okay, that was I would say directly proven in the Eurocrypt 09 paper. And if you look at the y-axis, so if you look at the final value of the PI, for example, this relates to the asymptotic informativeness and to the attack complexity, because essentially the number of traces that you need to attack with a given success rate is proportional to a constant divided by the information theoretic metric. And the constant essentially depends on the success rate that you want to target and the size of the key hypothesis that you want to recover. That was not actually proven in general in the Eurocrypt 09 paper. We had indications like experimental that it should work. We had proofs very rapidly for specific leakage models. For example, for unprotected implementations and Gaussian leakages, it's very easy to do, because then the information can be connected to the correlation coefficient or simpler metrics. But later, I would say it was generalized in two papers, one about masking and one specifically a chess paper in 2019 about these information theoretic bounds. Good. So what is the intuition behind this matrix? Essentially, what we can say then is that if you know what is the attack complexity, because it is fixed by design. You have a countermeasure, you have a mode of operation such that the key, any key that you manipulate, can only be reused, let's say 2 times, 3 times, because you have a rekeying everywhere. Then I would say like the security metrics are enough, because essentially what you care about is security against SPA, which stands for simple power analysis. So that means essentially you know already in advance how many traces you can exploit, independent of the success rate that you want to reach, and that is SPA and security metric will be very simple. Why? Essentially because I go back here. When I go back here, there's no need to cover the whole axis of the n values, because the n value is fixed. By contrast, if you are in a situation where the attack complexity is not known in advance, then of course you are in the case of DPA security, the DPA setting, and DPA stands for Differential Power Analysis. And then I would say IT metrics are very interesting because they provide a shortcut. Good. And this is why at that time, I would say when we were working on this matrix, we really saw this framework as a kind of middleware between models and device, or between theory and practice, if you want. And I will give 2 examples. One is the case of masking, which is of course a very important countermeasure where you do computation on secret shared data. Then masking, what proofs show essentially is that it requires some noise in the implementation in order to amplify the noise, essentially. And what we can show is that these noise assumption that we need in masking security proofs, essentially that depends on the information theoretic metrics, right? Information theoretic metrics are a good way to characterize the level of noise in the implementation. Good because it's quite general. It can work for any noise distribution that you want to consider. But If you look at other types of countermeasures, like on the bottom of the slide, I show some leakage resilient mode of operation where you do rekeying, right? You start from a key, you generate a stream and a fresh key. Then you are typically in this case where the number of traces to attack is fixed by design, and the leakage bound that they need in the proofs can be connected to security metrics. So both of them are useful, and both of them provide a way to quantify a little bit what are the assumptions that we need in security proofs. Good. So that was the that were the main ideas that we had in the paper, and we really listed many open problems, or we had many questions that we could not completely solve already at that time, which I would like to discuss now. Sorry, I will put the battery. Okay, so that I'm not shut off. Good. So one thing that is, I would say, nearly solved is the problem of security metrics. So what is the problem there is that if you take the success rate or the guessing entropy, it's very easy to estimate if you have an 8-bit subkey. So if you do a divide and conquer attack and the attack works perfectly, it's not so easy to do if you want to estimate the success rate or the guessing entropy for a 128-bit key, and you are not in the trivial situation where every key byte was completely successful. What you want to do there is deal with the situation where you had some information leakage and you could perform an attack, but at the end of the attack, you reduce the entropy of the key, but not completely. In order to deal with this situation, what the adversarial strategy, I would say, is to perform key enumeration. And what's the idea of key enumeration is you start to list the keys based on the probabilities provided by the side channel attack in decreasing order of probability. And what do we see here is that the first line here is the first order success rate, and then each time you multiply by 2. So this means that's the probability of the key being rated first among the 2 first key candidates, 4, 8, and so on. And what we see is, of course, that enumeration helps a lot, and you can really kind of compensate a lack of information in order to recover the key. That's still a situation where in the end you have enough enumeration power to recover the key, but if you're an evaluator and not an adversary, I would say you're not really interested to always recover the key. What you would like to do is to design an implementation such that it's not possible with reasonable computing power to recover the key. And therefore, we introduce this problem of rank estimation. It's really the dual of key enumeration, except that this time you know the key. And the only thing that you want to do is estimate very efficiently what is the position of the key in the huge list of 2 to the 128 possible keys. And you can do that quite efficiently with different algorithms, and that's the typical result that we call the security graph. So here on the x-axis you have the number of traces, on the y-axis you have the key rank, and you see that we are able to evaluate or to estimate key ranks for values that are close to 2 to the 128. I would say it's reasonably well solved because in the basic setting, like targeting a block cipher and divide and conquer attacks, we know how to do that. And there's no big problems of efficiency. It can be slightly different if you want to target asymmetric cryptography, where you have key dependencies, and of course you have many follow-up works and optimizations to make these things as simple and neat as possible. But I would say practically, these are things that we can do reasonably well. What is much less solved, I would say, and I even call this unsolved challenge, is the problem of information theoretic metrics. So what's the problem here? As I said, ideally we would like to compute the mutual information between a key and the leakage that is reflected by this equation. And essentially this mutual information, this can be viewed as a statistical distance between conditional distributions. And what we face as a problem here is that when we want, for example, to estimate the probability of the key given the leakage, we would like to have some information about what's the probability density function of the leakage given the key and to apply bias. But essentially, we don't know that, right? We have no clue what is the real leakage function of an implementation. And that's probably very, like, having the exact one, that's probably very difficult because circuits are complex. That means solving Maxwell's equations, and we rarely do that perfectly. So what we do as adversaries is to replace this true distribution by a model. And that's what we can do with the information theoretic matrix as well. And that's why we introduce this idea of perceived information, which is really the amount of information that you can extract from the leakage with an estimated model. And now it starts to be a statistical distribution, sorry, a statistical distance between a model, which is in red, and the true distribution, which is in blue. And that's exactly what the adversary does, right? He builds a model, he estimates a model, and then he challenges the model against true samples. Good. So you could say you still have a problem because the real distribution we don't know, but the good news is that this time the perceived information can be estimated by sampling in two steps. So in the first step, during the profiling or the training step, we estimate the model, and in the second step, we test the model against fresh samples of the true distribution. And essentially this is okay because this sum that you have at the bottom, the sum over a lot of samples of the true conditional distributions, this can be viewed as an integral by sampling. Good. What's the challenge then? It's essentially we would like to estimate the worst case security, which is the mutual information equal to the perceived information. And we know this never really happens in practice because it would require a perfect leakage model, and we don't know how to build that. So the evaluator question, which is reflected by the figure at the bottom here, is essentially to find out how large is the gap between the perceived information that we can compute in practice and estimate, and the mutual information that we never really know. We have partial attempts to deal with the problem, but nothing completely satisfying. I would say one qualitative attempt from Eurocrypt 2014 was to say that maybe we could say that the model is good enough if the assumption errors of the model are small in front of the estimation errors. And that would mean essentially you train the model up to a certain level, and you reach the point where, given the number of traces that you have, there's no interest to try to build a more accurate model, because anyway, what dominates is estimation error, so a lack of sample, not a problem with the model assumptions. How we could do that, for example, is by checking that the samples of the model and the samples of the true distributions, they are coherent. Here I show an example where the model is Gaussian, the true distribution clearly is a bit skewed, so it's not the same. What do we see informally by looking at the statistical moments of the distribution is that the mean and the standard deviation, they look pretty much the same, and actually they are. So it's not able to tell the difference between the two distributions by looking at mean or standard deviation, but we see that there's a big problem with the skewness and a slight problem with the kurtosis. So based on that, after a few measurements, we're able to say, okay, this model, this red model, it's not good enough. It doesn't correspond to the true leakage distribution, and you should try to improve it. It's quantitative because this is how it works, right? Essentially, would put now on the x-axis the number of training samples or of number of modeling samples. On the y-axis, you have the perceived information or the information theoretic metric you want to use. And what do you see is that at some point certification fails, which tells you, okay, with this amount of samples and this model, we can see clearly that the model is different from the true leakage, so please try to find a better model. But it really doesn't say anything about the size of the gap, and maybe there is indeed an error, but in terms of mutual information, it's extremely small and not so annoying. So we tried also more recently a quantitative attempt, and the goal here would be more to upper bound the mutual information thanks to the hypothetical information, and which is kind of the training information. This really only works for empirical distributions, but in theory, it's very nice, of course, that's a case where we simulated everything. The black curve is the mutual information. The red curve is the upper bound, this empirical hypothetical information. The blue curve is the perceived information. We see that we have a bound, we see that we have convergence, and so on. The problem is that this type of very nice result is not very useful in practice because we are limited on models, limited to models based on the empirical distribution, and they converge too slowly for the type of distributions we really care about, which are higher order and multivariate leakage distributions. Good. So far, I would say I didn't say much about how we actually estimate the model. Like implicitly, I was meaning that we were discussing models that were published at the time, so mostly Gaussian templates, LDA, and things like that. And of course, one big difference since 2009 is these huge advances in machine learning, deep learning, in general, but in particular applied to side channel security evaluations. You have a lot of efforts in this direction. And I'd like to discuss a little bit what is new there, and does it contradict what I said so far? Is it complementary, and so on? So starting point here is this nice paper from Piczek and co-authors at CHESS 2 years ago. And it's a paper about conflicting metrics for between machine learning and side channel attacks. And they explicitly say in the abstract, we show that machine learning metrics, and especially accuracy as the most often used one, can be extremely deceptive. So this is like suggesting that there's a need, or there is at least a metric issue. And the question is, of course, then, is it a metric issue that is raised by statistical learning or machine learning, or is it something that we could already observe previously, and then it would rather be related to the context, right? Whether it's SPA or DPA. And to answer that, I think it's nice to look back at a result that we had 15 years ago, where we were exactly trying to discuss these metrics issue, right? We kind of figure out the same thing. It was not accuracy, it was the success rate, but I would say success rate is as close as can be from accuracy, especially if you take n equal to 1. And what do you say? It's the success rate for two types of countermeasures. I think the details are not very important. Let's call them the red countermeasure and the green countermeasure. On the left, you see the full curve. And clearly, you could say, okay, based on the full curve, we can see that the red countermeasure is easier to attack than the green countermeasure because you need more traces to recover the green countermeasure with high success rate. But if you zoom at the very beginning of the curve, where you have limited number of leakages obtained, what do you see is that then it's the opposite. Like the green countermeasure is slightly easier to recover than to break than the red countermeasure. What's the problem here is it's essentially expected because the number of traces that you need to recover the key with a high success rate, this one is not known a priori. Right, and that's, if you think about it, it's exactly what motivated the introduction of information theoretic metrics. So essentially, I would say what we see here on this figure is the same kind of problem that we face with the accuracy and machine learning. So if I go back to the question, do we have a metric issue specific to machine learning, or is it related to the context? Like SPA versus DPA, the tentative answer is really, on the one hand, it is true that accuracy, which is a security metric, can be deceptive in side channel analysis and in evaluation. But I would say the reason it's not really the fact that you use one or the other statistical learning tool, so the fact that you use machine learning or deep learning, it is just the context, whether you are in the SPA or DPA context. And if you are in this DPA context, indeed, it's not the right metric. So at least I would say this connects to the lessons from the past part of the title. To me, it shows that this idea that we should use security metrics for SPA evaluations when we know the number of traces that we have to attack, and IT metrics for efficient DPA evaluations where we don't know this number in advance, this I think remains completely true for machine learning, for deep learning, and it's probably true in general. And typically a corollary, which you can read in a paper by Loïc Mazur, Cécile Dumas, and Emmanuel Proof 2 years ago, is that IT metrics are in general good loss functions if you want to perform DPA. And I think in general, the right loss function should be connected somehow to one or the other kind of IT metric. By contrast, so I would say machine learning and deep learning do not raise the need of new evaluation metrics. What they could be extremely useful to is to bridge the gap between these worst case and the practical security evaluation. So if you remember, I had this slide with the wall saying we in academia mostly we try to evaluate what is the worst case security, what is the best attack that can be mounted, and we had this more practical question of how can we mount the attack, what's the cost of the attack, what are the capabilities of the adversaries. And when you look at the literature nowadays, I would say this question of worst case versus practicality, what mostly define the two types of attacks is the capabilities of the adversaries. For example, the fact that the adversary has implementation knowledge, the fact that he can profile with known randomness, the fact of whatever, that the adversary can really use all information possible. And therefore, one very nice track for research, and what's a big challenge in my opinion, is to formalize a little bit this idea that machine learning can sometimes do in a black box context what worst case attacks do with more capabilities. And on the figure here, I show these information theoretic metrics, the what's the column? Cyan one, the light blue one here on the left. This is really the worst case thing where the adversary has all the information. The black one is MLP, so multi-layer perceptron. What do we have? We have a Gaussian template here, and you have different levels of assumptions about the leakage function. And the more you assume about the leakage function, of course, the easier is the task to find out a good leakage model. Of course, if the assumption turns out to be wrong, maybe we will not converge towards the right value at all, but that's not what we see here. And that's really, in my opinion, is the challenge for the future part of the title. What would be extremely interesting is to formalize this gap or this lack of gap between worst case security evaluations and practical security evaluations, to know a little bit more what one says about the other and so on. And I would say deep learning, in particular deep learning applied in a black box context with good convergence properties would be the natural tool for that, and seems very, very promising. Good. So what time? Yeah, it's more or less time to conclude, I guess. What I wanted to say, like first about the past, the conclusion would be that I think what the main reason why we introduced this framework 15 years ago, which is about separating IT metrics and security metrics, that remains quite useful to structure evaluations, because it helps you if you want to compare implementations, if you want to compare adversaries, it tells you what's the right metric to use, right? To use information theoretic metrics for implementations, security metrics to compare adversaries. It's also giving us this intuition about SPA and DPA, right? Information theoretic metrics. They are more useful in the DPA setting, because then it can make the evaluations faster and more intuitive. And the other hope that we had, and I think this proved to be quite correct, is that they could serve as an interface with security proofs. Like, as I said before, IT metrics are quite useful for masking, security metrics for leakage resilience. Conclusions for the present. What I didn't say too much or didn't explain, but the other reason why IT metrics are interesting is that they can be a very helpful proxy before proving the security of a countermeasure and checking the tightness, maybe. Here I show on the left what we have with masking. That's in a paper from 2010, where we evaluated the worst case security level of a masked implementation with these IT metrics. The x-axis is the amount of noise. in log scale. The y-axis is the number of traces that you need to attack. The blue curve is an unprotected implementation. In red, you have first order masking, so 2 shares. In green, 3 shares, and in pink, yes, 4 shares. And what do we see? We see both that if you don't have noise on the left of the curve, there's no security. And second, that when you amplify security, the amplification is indeed exponential. And there's a tight link between the number of shares and the slope of these information theoretic curves. So what's interesting is that this was studied for many years, I would say. Like the masking was introduced in 2000 and something, or 98 even. We did these information theoretic evaluations in 2010, and at that time it was not proven, right? It was to show that there's an indication that these things are tightly connected. Finally, it was proven in 2013 by Proof and Rivin. And I would say their proofs is still, if you remove idealized assumption, it's still not completely tight. And even today, tightly proving the security of a mask implementation is something quite challenging, probably requiring advanced leakage models that are still under investigation. But if you remove masking, if you look at other countermeasures like shuffling, we could do information theoretic evaluations that gives indication of what is the security that they provide. We don't have much proven yet. We have the same for horizontal attacks, right? There are gadgets like multiplication algorithms that are secure against very advanced adversary who try to reduce the the noise in the leakage. It's very difficult to analyze this with standard tools because we really need to reason about the noise level that we don't have in abstract models like the probing model. And we can already show by information theoretic evaluations that it seems that these gadgets have good noise rate, have good security against horizontal attacks, and that gives us indication that this is really something we should try to prove. Obviously, the combination between masking and shuffling is the same, and so on. And then future, of course, is what I said already, right? I mean, in general, long-term security is hard to anticipate. That's a problem that we always face. And you can choose, of course, you can say, okay, I am going to do security evaluation in a closed source setting, and I will take a lot of time to find out what's the security level of my implementation, probably losing a nice way to anticipate what an adversary could be trying to do. If you give yourself the means of doing open source attacks, you will see the security decrease faster, which may look a bit negative, but you will have much more rapidly an indication of what is the worst case security level, which means you will limit the risk of bad surprises after the deployment of a product. And in general, this anticipation, I would say, is interesting for designers and much easier in an open setting. The problem that we have here, and that's really, I would say, in the future for sidechain security evaluation, one of the main questions is, do we have a gap between these two approaches? Can we perform with a closed source attack, exploiting good machine learning, deep learning algorithms, the same attacks as we can do in open source? And as a concluding slide, I would like to add this one, saying all this is much more showing that there's good connection, or there should be connection between theory and practice, rather than seeing an opposition between both. And that's true both if you think in terms of designer and if you think in terms of evaluator. As a designer, I would say we should always try to push cryptographic formalism, which essentially means transparency and definitions and sound tools as far as possible. Why? Because this gives us confidence, this gives us all the success that we had in cryptography, and that allows us to really have a separation between unambiguous assumptions and proofs. And I think it's clear in the physical security setting, we will never be in a situation where everything is nicely provable, right? We will always have physical assumptions that needs engineering, evaluations, measurements, and so on. But it's of course much nicer if we can limit those to something well understood, to a clear challenge, well defined, and so on, and ideally to a limited number of such assumptions. That's for designs, and I would say for evaluation, probably a good approach is the same, right? We could completely try to combine this open approach and the practical approach that the industry is currently leveraging by starting worst case and then study what happens when you relax adversarial capabilities. And that's what we denoted with a big group of people as backward security evaluation 2 years ago. And I think that's it. I've been long enough, so I'll be happy to answer any question if you have. Thank you.
Thanks, Alex, for this nice talk. And any question from the audience? You can unmute yourself and you can jump.
Hello, Professor FX. Thanks for the nice talk. This is Shaindip Shah. So I'm now at NTU, but I was a student under Professor Mukhopadhyay. So I have a question, like when you go back to the concept of perceived information, so there we see that we have some model and then we have the leakage and we try to fill up the gap, basically. I mean, more we fill up the gap and I mean, it's better, right? So, I mean, is there any possibility of creating that model? So usually I think we take a Gaussian. So is there any possibility of creating that model using machine learning? I mean, a better noise model using machine learning?
Yes. So machine learning, typically I would say right now, if you do something completely Gaussian, I think it's okay for unprotected implementation. We know pretty well that it's not going to be okay for masked implementations, right? Because we know when, I don't know if this example, right? That's not a completely invented example, right? This skewed distribution, this is really the distribution of a masked parallel implementation. So the Gaussian assumption is not good here. And as long as you stick with Gaussian, you will not be able to attack. So Gaussian is great when you can do it because it cannot be faster, I think, but it's not going to be general enough. The other extreme is this thing there where I say, okay, we could use the empirical distribution, but that's perfect from the, I would say, assumption error viewpoint, but it's so slow in converging that it's not very practical. I think machine learning has a good potential to be just in between, with huge amounts of challenges, because of course setting up all the parameters, there's a lot of black magic, at least from my viewpoint and from the experiment we performed, probably due to lack of understanding and need of more work to set everything up. But in the long term, yes, I think you're completely right, and that would be very interesting.
Thank you for your answer. And another small question is regarding the SPI attack. So nowadays we see like single trace attack are quite prominent for you know, even in public key setting like post quantum and even in private key setting also. So I mean, the metric that we usually use, as you mentioned, the Q simulatability or those kinds of concepts, right? That I can have at most Q traces and then I can formalize if I can attack with Q traces. So I mean, but I think a general or common situation can be that, okay, I have some measurement setup A, and with that probably due to some noise, I can only create the model with say 4 traces and I'm good. But say I just improve the model, or I just improve the measurement setup in near future, and it reduces to 2 simulatability or something like that. So I mean, is there any way to extrapolate that, okay, I have this kind of noise and I do SPI attack with this kind of trace acquisitions and all, and later to, I mean, so if I just reduce the number of traces and I mean improve the noise to this level, then the number of traces might reduce. So is there any kind of this kind of extrapolation mechanism available till now? Because I understand that SPI is more about noise than anything else, right?
Yeah. So high level, I would say, like, of course, SPA is easier to prevent than DPA because it gives less to the adversary. Unfortunately, I think SPA is also much harder to evaluate than DPA. The reason is that when you do DPA, essentially DPA depends on DSNR, right, on the mutual information, so signal and noise. When you move to SPA, in most of the cases, I think that the basic SPA attack that everybody has in mind is SPA against AE schemes in decryption. There, the adversary can repeat the same, even if you're bounded to 2 values, you can repeat the decryption again and again, which means you can remove the noise. And now the problem is that this SPA security doesn't depend on the noise or on the DSNR. It really depends on the shape of the leakage distribution, on the deterministic part, which nobody really had studied very carefully so far. So that that essentially implies that at the moment, I mean, I would love to have an extrapolation, as you say, for SPA security. I don't think we have it, or I don't see any paper that found something easy to characterize, which helps us to say, okay, increase this security parameter, and then SPA security improves in those lines. While
Yeah,
for
so
DPA, you would do the noise, right? DPA, you double the noise, you divide the SNR by 2, and you're happy with that. I don't know how to do that with SPA.
Right. So that can be a important research direction, I think.
Yeah, totally.
Thank you for your answer.
I think you're muted.
Okay.
Yeah.
So I have a question. Is like this kind of analysis, right, which is done for evaluating the side channel attacks, particularly. How do you think they are extensions to like other kind of physical attacks, like maybe fault attacks, for instance?
So conceptually, I think it's close, right? If you see, I mean, of course, like take differential fault attacks, you can easily quantify what's the amount of information that a fault gives you. The problem is essentially it's even more powerful, right? How can we say that? Like, imagine that you do a bit flip fault against one 8-bit S box. You have 8 bit of entropy, but after 1 bit, you have 8 keys left. So that means 2 to the 3. You reduce the entropy by 5. So the mutual by 5. The mutual information is essentially 5. That means in 2 such faults, you're dead. And when you go for 32-bit faults and so on, it's essentially the same idea. So the theory remains the same. It's less clear. I mean, it's even more extreme that you should not tolerate any fault, because as soon as you have 1 or 2, you lost too much entropy, I would say. As long as we stick with these fault models that we know, which is also, I mean, all these efforts on characterizing faults, like the profiling part, but for faults, would be quite interesting. Which makes me think about a Eurocrypt paper, like the profiled fault attacks and so on. All this is very interesting. But I assume we would need to make the all these evaluation less black or white. We would need to make the faults less damaging in the first place, so to prevent that these very strong patterns appear.
So you mean to say like the countermeasure should be able to kind of ensure first that the faults are not so significantly damaging, right?
Yeah, because we do, with leakage, we do 2 things, right? We reduce the information for one point in time, and then we do some kind of amplification. But we really need to, like, there's one part is the engineer's part, like you need to reduce the information, and then there's a math part, you need to be able to amplify. And both are difficult, but we see how to do both, with noise for reducing information, with masking, for example, or with wikeying to amplify. With faults, it's how would you reduce the information of a fault in the first place? I don't know. And then if you can do that, then obviously rekeying. I suspect for some types of faults, leakage resilient, like modes of operation or block cipher structures that are well suited to, like, and it started, right? You have this default paper, you have the Fried paper. I'm not saying it's completely perfect, but it gives clear indication that there's a way to design the primitives to improve faults, which is good. I think we can do the same with mode. I still don't see, I think we know less at the implementation level, and that would be super interesting, right? Go more on the type of profiling the fault models, understanding, and maybe doing the technology so that the faults that appear, they are not so destructive in terms of reducing the information.
So just a question, like in fault, like in side channel, we have the masking order, like we can quantify the protection order. But similarly in faults, we can do something like that, right? I mean, a second order, I mean, I can prove security against 2 faults to prove security against more than one fault like that. So do you think that, I mean, that can be the first step towards the quantization? Because, I mean, default is slightly different, but freight also provides security against single bit faults. All kind of single bit faults. Okay. So can that be a direction where we can formalize and, I mean, eventually come to this direction, you know, for proving the security?
I think so. So at least for basic, the question then I don't have the answer, but for I would say the standard differential fault attacks, this seems a right approach. Then you had these CIFA type of things.
Yeah.
For those, it's less clear to me because I think what you have in mind is then some kind of encoding, but these encodings do not seem so effective against this CIFA thing.
Yeah.
So,
CIFA and
but
then
yeah.
forwarding combined attacks. Yeah.
Yeah. So, but yes, for really the standard differential fault attacks, I mean everything but CIFA, this seems like a decent security parameter. Okay, I can resist 1 fault, 2 fault, or 1 bit fault, 2 bit fault, and so on. I also, I mean, the questions are how accurate can you be, right? How many bits can you fault and how precisely? And probably how easy it is to repeat twice the same fault. Like if you should, because if you can repeat twice exactly the same fault, it seems to me that there's also a lot of these redundancy-based things that will not work.
Yeah.
Maybe not at all, or maybe not as expected at least.
Okay. So, any questions from other members in the audience? Okay. So, FX, one final question. I mean, there are some works which also does to. I have some. It's like like we read from the papers, right? People try to propose tests like TVLA or like statistical hypothesis tests to certify. So we know of like some of your papers that we have seen, like how not to use those kind of tests. What is your general opinion about like because in industry some people probably like try to use those approaches, right? So what is your like opinion on that?
So I would say I would use them as a way to test the security order and nothing else than that. So I think to me they work well when they tell you, okay, I see a problem at this security order. And then you try first, second, third, and you see the one that leaks most. That's okay. That tells you what's the effective security order of your implementation. I think that they are of very limited interest when you don't detect. That's the general viewpoint. You have a lot of thing. Elisabeth Oswald would be a better person to ask. Right? She really works extensively to argue about what's the limitations of TVL. I'm probably more dogmatic about it, and I don't think it's in general a good approach to evaluate security. I would directly go for worst case because I like things being quantitative. But again, if you, as part of a worst case security evaluation, it is important to assess the security level. As a standalone security evaluation tool, and we know it's risky, right? I don't want to be overly negative because there's also, I mean, it's better than nothing. It gives indication. I think that there's a big potential for misuse. And even in the academic literature, it was easy to spot misuses of this TVLA thing, where I think it would be much more interesting to combine it with something quantitative, and that's it. But that's.
In one of our works, we tried to kind of combine this TVLA with the estimation of success rate, but it seemed that estimation of the leakage model was the main, like I would say, like challenging problem, right? I mean, as you point out as well.
Yeah. It's a kind of trade-off, right? I mean, in the end, it's number of traces, like, because in the end you need to, let's say you have 256 possible values. TVLA essentially says, okay, let's just estimate 2 and see what happens. That's good if you're lucky with your 2, but it clearly doesn't tell you. I mean, you don't know the SNR as long as you didn't estimate the 256 means or the 256 leakage models. Whether the one that you did not estimate is the one that's going to kill you, it's maybe not the case, but like it's gradual, right? With 2 classes, I think you can lose a lot. With 256 classes, maybe it's too expensive sometimes. Whether the intermediates are interesting, I don't know really. It's obviously right that we are in a very, like, it's expensive to do all these evaluations, even the deep learning things, like that's, even if it turns out it is possible to do in black box what we do in worst case, it's still, I think that there's a nice paper on ePrint about the CTF that we had last year at Chess, and it's BSI people who launch these deep learning things, and they really make their machines run for the whole summer to have a very powerful attack, but and their attack is slightly better than ours, so that you see that machine learning will catch some details that we don't see. Is it really worth the price, like as an evaluation, to do all these efforts, or I don't? Yeah, these are hard questions, right? But that's where, if we could characterize the gap between these things, have a better understanding of what we can miss, that would be very interesting.
Right. Yeah. So I think there are no more questions from the audience. So thanks, Avex, I think, for this nice talk and for your sharing your time and views. Maybe we will try to get back to you with further queries, I mean, as they come up. And I'm actually planning to visit Belgium this month. If it works out well, then maybe I'll try to kind of drop by.
Right. Yeah. If you're in Belgium, send me an email and pass by in Louvain. Yeah, that would be nice.
Planning to visit UCLouvain, but still not got the visa interview. So let's see how.
Good luck.
Travel is getting more and more difficult actually. So hopefully things turn up. So thanks, Avex. I mean, I think on behalf of Computer Science Department, we would be very happy to, like in person at some time invite you. But as of now, this is what we have. And thanks a lot. Yeah. Thank you.
Thank you. Thanks for the invitation. If anybody has any question or wants to send email, just I mean, you feel free to react.
So the slides, is it possible for you to share the slides? I mean, then I can share the audience as well. Yeah.
I can share the slides, of course. Yeah.
Thank you. So thanks a lot.
Thank you.
Thank you.
See you. Bye.